So now let's learn of a bunch of very interesting concepts, right? First we'll start with a concept called the cofactor matrix, right? So we'll start with the first concept called the cofactor matrix of a given matrix A, right? Here of course A is a square matrix. So given a square matrix A, what does the cofactor of this matrix basically mean, right? So let's go step by step, right? So let's take a simple example, probably that's better. So if you take a matrix A which looks like this, which is let's say a 3 cross 3 matrix with 1, 4, 7, 3, 0, 5 and let's say -1, 9 and 11. Okay, let's assume this is my matrix A, right? So I'll start creating something called as a cofactor matrix as follows. Okay, so my cofactor matrix, I'll represent it as C, right? So this is the cofactor of matrix A. This cofactor matrix also is 3 by 3 because your A itself is 3 by 3. Okay, your cofactor matrix is also a 3 by 3 matrix. But here starts the fun. So since it's a 3 by 3 matrix, it will have 9 elements. Okay, it will have 9 elements, right? Let's say the first row, first column, let's call it C11. First row, second column. First row, third column. Similarly, 21, 22, 23, 31, 32 and 33. Okay, so if I want to obtain the value of C11, if I want to obtain the value of C1, what do I do? It's a very simple concept. Okay, I'll write -1 to the power of, I have 1 and 1 here, so I'll add these two. Okay, it's -1 power 1 plus 1. Okay, and now I'll compute the determinant of, because it is the cofactor corresponding to the first row and the first column. Look at this. This is a cofactor this is a value of the cofactor matrix corresponding to the first row and first column. So I'll ignore the first row and the first column. If you ignore the first row and first column of A, what do you get? You get this smaller matrix. Okay, so let's take the determinant of this matrix, which is 0, 5, 9 and 11. Right, we discussed in the previous video that this is called the minor. So we discussed in the previous video that this determinant is called the minor of matrix A. Okay, this is often represented as M11. Okay, in many textbooks this is written as M11 to represent that this is the minor obtained by dropping the first row and the first column. Okay, so this is what your C11 would look like. So this gives us a number, right? Because this is a determinant, it gives us a number. This number you multiply with this number to obtain C11, which is a number. Again, right now I am explaining these concepts numerically. I will also give you some geometric interpretation of some of these concepts as we progress. First, let's look at it numerically. Then I'll connect all of these concepts to a very interesting geometric representation. Okay, so first let's go through it numerically. Okay, so that it makes simpler. Okay, similarly, if I want C23, what do I get? So second row, this is my second row. Okay, so drop second row, drop also third column. See, I'm dropping these two, right? So I get -1 to the power of 2 plus 3. 2 plus 3 multiplied by drop second row and third column, right? What are you left with? 1, 4 minus 1, 9. So this is what you get. -1 and 9. Okay, this is the value of C23, right? Similarly, you can obtain the values of each of these 9 cofactor values and hence obtain the final cofactor matrix A itself. Okay, so generically speaking, the value of Cij is -1 power I plus j. The value of any ij, ith row and jth column, is -1 power I plus j into determinant of, or to be more precise, you can actually write it as Mij. Okay, Mij, because Mij is the minor obtained. What is a minor? Minor is the determinant of the matrix that is obtained by dropping the ith row and the jth column. Okay, so that's what this is how you can write very succinctly or very simply or very cleanly or very briefly, right? This is how you can explain the concept of a cofactor. Again, right now I'm only explaining you some numerical concepts. I promise you that I'll connect everything finally to a very interesting concept called the inverse of a matrix, which has a very, very interesting geometric interpretation, and it's a super powerful concept, right? So the whole idea of coming up with these concepts like cofactor, okay, so one of the biggest applications of this concept called cofactor matrix is in computing inverse, which has tons of applications itself. Okay, so the concept of inverse of a matrix has both geometric interpretation and it has tons of applications, tons and tons of applications. We'll see some applications as part of this course itself in detail. Okay, So since we have understood this, right, since we have understood what is the cofactor of a matrix, let's understand the next concept, okay, which is called the next concept is called the adjoint of a matrix. Okay, so the next concept is called the adjoint of a matrix. Adjoint is slightly an older term used for it, but people have started not using this term very often more recently, because it gets confused with other terms in linear algebra. The more popular term that people are using nowadays, like when I was studying linear algebra as a student, adjoint was the more popular term, but it gets confused with other terms in linear algebra and mathematics. So people have started using this term called adjugate or adjunct. Okay, so these are terms that are more popular in more recent textbooks. Okay, so adjoint of a matrix is often written as adjoint of a matrix A, is a very simple concept. Okay, again, the whole idea of coming up with the concept of adjoint or adjunct or adjugate of a matrix is again to compute the inverse of a matrix. Okay, so all these concepts that we are learning, whether it's a concept of a cofactor matrix or a minor matrix, of course there are some applications of cofactor matrix and minor matrix itself, but the most important and the easiest and the most powerful application of cofactors, minors and adjoints, right, is to compute the inverse of a matrix. Okay, this is super duper important. Okay, now let's define what is adjoint of a matrix. Okay, adjoint of a matrix or adjunct of a matrix is very simple. It is a transpose. It is nothing but C transpose, where C is the cofactor matrix. Okay, so this is nothing but, this is the transpose of the cofactor matrix. The cofactor matrix of A. We have seen how to compute the cofactor matrix of A, right? So you take the transpose of the cofactor matrix and you take the transpose, instead of writing it in curly braces, instead of writing it in square braces, let me put in just simple braces. You compute the cofactor of A as explained here. And again, remember, to compute cofactor of A, we are going to use minors of A. So the way it works is, to compute inverse of a matrix, we need to use adjoint or adjunct of a matrix. And to compute adjunct of a matrix, we need to compute the cofactor, because adjunct is nothing but cofactor transpose. And to compute cofactor, we need the concept of a minor. Okay, I hope you got this sequence of logics on why we are learning the concept of a minor, why we are learning the concept of a cofactor and the concept of an adjoint. Now inverse itself, as I told you earlier, has a ton of geometric applications, and more importantly, many real world applications in science and engineering, right? So I hope this reasoning on why we are learning these concepts is clear. Okay, so with that reasoning, let me take a step forward and let me also define. So this is one way of defining adjoint of a matrix. There is another popular way of defining an adjoint of a matrix. So this definition helps you compute. This definition helps you numerically compute. So this definition helps you numerically compute the adjoint of A, because you can compute the cofactor of A numerically using minors. So in the numerical computation, adjoint of A, if you want to compute the numerical value of adjoint A, using the cofactor based formula or cofactor based idea is a better one. But there is also other intuitive way of, there are other definitions of adjoint of A. So the way it works is this. Okay, so the other definition of adjoint of A is this. Okay, if you have a matrix A, if you multiply A with adjoint of A, remember that A is an n cross n matrix and adjoint of A is also n cross n matrix, because C itself, the cofactor matrix itself, is an n cross n matrix, right? So this is an n cross n matrix, this is an n cross n matrix. So other definition of adjoint of A is that matrix which you multiply with A to obtain a matrix like this. Now what is this? This is a scalar, right? This is just a number. This is just a number, right? This is just a number. What is I? I is your identity matrix. 1, 1, 1, rest everything zeros. This is a 3 cross 3. Okay, just instead of writing 0, 0, 0, 0 here, I put a big 0 here to represent that. Everything else is 0. Okay, that's what your I is. Okay, look at this, look at this. So what is it saying? It is saying, so other definition of adjoint of A is, adjoint of A is that n cross n matrix which when you multiply with A like this, what you obtain is, so what is this? So det of A into I, what would this be? If I is this, what would det of A into I look like? It would look like this. Det of A, on the diagonal elements you will only have det of A, rest everything will be zeros. right? What is this? We saw this to be a scalar matrix, if you recall. This is a scalar matrix. We defined what a scalar matrix is, right? Okay, this is where this concept of a scalar matrix is powerful. So adjoint of A is that matrix which when you multiply with A, you get a scalar matrix where all the non-diagonal elements are 0 and all the diagonal elements are equal to the determinant of A itself. This is another way of defining adjoint of A. Okay, very cool, very cool. From this there is a very nice follow-up that we can make. Look at this. If you think intuitively, right? If you think intuitively, I can rewrite this because this is just a number, right? This is just a number. So I can divide both sides by a number, right? So I can write this as A into adjoint of A by A. Remember that A is a number equal to I. Now if you look at this matrix, remember that this is also a matrix because adjoint of A is an n cross n matrix and you're dividing each of those elements by a scalar or by a number called determinant of A. Remember the determinant of A is a number. Let's not forget that. Now here comes a very interesting concept. Okay, so let me walk you through a slightly different concept in simple algebra, right? In simple numbers, right? Everything that we learned, not about linear algebra, simple algebra. Suppose I have a number 2. To which number should I multiply 2 to get 1? Right? I have to multiply 2 with 1 by 2. And here 1 by 2 is called the inverse. 1 by 2 is called the inverse or the reciprocal in mathematics, right? Probably you learned this in your 5th or 6th class, right? So 1 by 2 is called the inverse or the reciprocal of 2. Similarly, if I have a number 1 by 3, what number do I have to multiply 1 by 3 with to obtain 1? I have to multiply with 3. So 3 is called the inverse. So 3 is called the inverse of 1 by 3. If you invert 1 by 3, what do you get? You get 3. So in simple algebra, if you have a number x, right? Any number, if you multiply it with 1 by x, you get 1. And you might have noticed that this 1 by x is often written as x power minus 1. Right? If I want to represent 1 by x, this is something that you probably learned in your high school, right? So anything that you multiply, so x multiplied by 1 by x equals to 1. Or in other words, x multiplied by x power minus 1 equals to 1. Okay, this is the concept of an inverse. That's why this is called the inverse of x. Similarly in linear algebra. Now let's go to linear algebra. Okay, let's go to linear algebra. In linear algebra, if you have a square matrix A, right? If you multiply it with another matrix such that you get the identity matrix, because 1 in algebra is very similar in idea to I in linear algebra, right? I is nothing but your identity matrix. I is nothing but your identity matrix, right? So now the question here is, with what matrix? With what matrix? So the matrix that I multiply A with to obtain the identity matrix is called the inverse of A. Is called the inverse of A, which is often written as A power minus 1. Just like this, just like numbers, this is written as minus 1. Now comes the fun part. What is this matrix going to be? If I want to obtain this matrix, how do I obtain it numerically? Okay, again, we'll understand about the inverse of a matrix from a geometric standpoint little later. But let's look at it from a purely algebraic standpoint now. Purely numeric standpoint. Right? Let's look at it from a purely numeric standpoint first. Okay, so what will this be? If you notice this, when I multiply A with adjoint of A by det A, remember this matrix is also an n by n matrix, right? I am obtaining I, which means A inverse, if A inverse is defined as adjoint of A by det A. Okay, this is what I write it as, because we have seen here, right? We have seen here, this is the definition of adjoint of A itself. So here we're defining adjoint of A like this, and when I modify this slightly, I get this. Simple. I divided both sides by det of A, and I got this, right? Now, I can define the inverse numerically. Again, this is the numeric definition. I can define numerically the inverse of a matrix A to be adjoint of A by det A. But there's a small catch here. If det of A equals to 0, what happens? If det of A equals to 0, the denominator becomes 0 and this whole thing becomes not defined. Right? This is no more a valid matrix. Right? Because you're dividing all the elements of the adjoint of A by 0. And division by 0 is undefined. Right? So now look at this. Because det of A by 0, so if det of A equals to 0, then the matrix is said to be non-invertible, right? If the det of A is 0, if det of A is 0, the matrix is said to be, then A is not invertible. Otherwise, A is said to be invertible, because we can compute this A inverse function numerically by computing adjoint of A. And to compute adjoint of A, numerically, we need to compute the cofactor of A. And to compute cofactor of A, I need to use the minors of A. Okay, that's the flow of logic here. Okay, I hope this is clear. Okay, this is extremely useful concept. Again, we will keep using A inverse tons of places. So there is a whole application that we will dive into later in this course. It's called the system of linear equations, right? So I've described about system of linear equations, right, where you have some chocolates and things like that. I explained this to you in the introductory video, right? I explained this to you in the intro video. To solve system of linear equations, you need to use A inverse. Okay, that's one of the simplest and the most fundamental applications of A inverse itself. Okay, so if A inverse, so this is true if det of A is not equal to 0, which means if the matrix is invertible, then the matrix inverse can be computed by taking adjoint of A by det A. Okay, very, very simple concept, nothing very fancy here. Okay, so now let's go into the geometric interpretation of inverse. Okay, so this will help us get geometric interpretations of lots of concepts. So what does the geometric meaning of inverse mean? Okay, so let's take a very simple example here, right? Suppose I have a vector V, okay, and I've made a linear transformation on V. Okay, let's assume V is, let's say, a 2D vector or 3D vector. Let's just simply say it's a 2D vector for simplicity. Okay, so I have a vector V. Okay, so I have a vector V now, okay, which I'm performing a linear transformation through matrix multiplication, and let's assume I obtained a vector U. Okay, so I obtained a vector U by transforming vector V using matrix A. Okay, so this is my linear transformation. Now the question here is, with what vector? Now the question here is this. See, so we obtained U by applying the transformation represented by matrix A. This is how we have done it, right? Now the question is the other way around. What matrix transformation or what linear transformation should I apply? What linear transformation should we apply on U to obtain? What linear transformation should we apply on U to obtain V back? Or in other words, see, from V I got to U by using the linear transformation represented by A. Now the question is to come backwards, to start with vector U and to obtain vector V. Okay, look at it the other way around, right? What transformation should I use? The transformation is nothing but A inverse. Okay, so the inverse of a matrix is that transformation. See, the answer to this question is the A inverse. Okay, this is the geometric interpretation of it. Okay, so if you are given U and if you want to obtain V, okay, see, look at this. From V to U, we obtained U from V using the linear transformation represented by matrix A. But to do it the other way around, I need to use the transformation called as A inverse. This is the geometric interpretation of the inverse of a matrix. Okay, so let's look at it from an algebraic standpoint a little. Okay, so now I have AV equals to U. Okay, now on both sides, if I apply this transformation called A inverse, remember that this is also a vector, okay, so if I apply this transformation represented by A inverse, look at this, if I apply this transformation as represented by A inverse, and I can compute A inverse using this formula, right? This is the numeric this is how you numerically calculate the A inverse. And today most of this numerical computation is done by computers using a bunch of very, very powerful and elegant algorithms. Okay, so while some textbooks force you to solve it manually, in the real world we often solve this using computers and not by hand. Okay, so you have A inverse AV equals to A inverse U, right? That's what it is, right? See, remember I'm multiplying this, I'm pre-multiplying with A inverse, I'm also pre-multiplying this with A inverse. Now we know that A inverse AV, from the properties of matrix multiplication, we know that this is same as A inverse A into V, which is equal to, what is this? From the definition of what A inverse is. Look at what is the definition of A inverse. The definition of A inverse is that A into A inverse equals to identity matrix. Okay, so this is nothing but I into V. What is I into V? Is V itself, because I is an identity matrix. So V is equal to A inverse U. So now if you think about it logically, we can arrive at U from, we can arrive at V from U by applying the linear transformation as represented by A inverse. Okay, I hope these simple steps have helped you absorb this concept better, and the geometric interpretation is extremely important. It's a super powerful concept. Okay, now what is the geometric interpretation of adjoint of A? Okay, look at this. So it's slightly hard to give an exact simple geometric interpretation of adjoint of A, but what is adjoint of A? You can write adjoint of A as det of A into A inverse. You can write it this way, right? Now look at this. What does this mean? What does this mean? This means first you are applying the inverse transformation and then you are scaling it with a constant. Remember that this is a scalar, right? This is a number. This is a scalar or a number. So you can interpret adjoint of A as an operation wherein you are applying the inverse transformation of A itself and then scaling everything by this number. Okay, that's one way to interpret the adjoint of A geometrically. Okay, so now let's go and look at some very interesting properties one by one. Okay, the first very interesting property, again, some of them I'll prove numerically or algebraically. So some of them I'll prove algebraically using simple linear algebra. Some of them I'll try to give intuition using geometry. Okay, wherever I can. Okay, wherever geometric intuition is easy and simple to follow. So for example, let's say I have this det of A inverse. Okay, what does this mean? Okay, what does this mean? We know what A inverse means, right? It's the inverse operation of A. And what is det of A? Det of anything. So we saw the det of any matrix A is the area of the parallelogram, geometrically, that is created by I1 hat and J1 hat, right? So imagine initially in my original space I have I and J hat, right? Their area that is covered by these two is 1 unit, because the length of I is 1 unit, length of J is 1 unit. Now if I performed a transformation of this space using matrix A, suppose the area of the parallelogram became 3, which is the area of the parallelogram between I1 hat and J1 hat that we have seen earlier, right? So what is now det of A? Det of A is, so what does this mean? This means det of A equals to 3. Now what is A inverse? A inverse takes you, remember that A inverse takes you from this space back to this space. So to go back to I and J space, I hat and J hat space from I1 hat and J1 hat, you would perform the A inverse transpose. And when you perform the A inverse transpose, because the area got tripled here, look at this. Let's assume while going from I hat and J hat to I1 hat and J1 hat, let's assume the area got tripled. The area of the parallelogram tripled literally. Now when I go back, what happens? The area should get 1/3, right? Because this tripled, I'm going exactly the opposite way. Here I'm going forward way, here I'm going backward way. Hence, A inverse should be 1 by det of A, which is equal to 1 by 3. So this is equal to 1 by det of A, which is also sometimes written as det of A power minus 1, because det of A is a number. Remember that det of A is a number. This is like saying 3 power minus 1, which is nothing but 1 by 3. Okay, so I hope, see this proof, again, you can prove this mathematically also. You can prove this numerically. Trust me, you can prove this numerically. But the numerical proof is very, very tedious, because you have to now use cofactors, you have to use minors, you have to use adjoint, all of that stuff. Thinking about this proof geometrically, using det of A as the area of the parallelogram and inverse as the inverse operation to reverse a transformation. This is a much more elegant and simple thing to argue about, right? So this is a very elegant way of proving that det of A inverse is 1 by det of A. Okay, so let's go to the second interesting theorem. Okay, which is, okay, let's actually work it out. So what is A inverse? A inverse is adjoint of A by det of A. right? This is by definition. This is by definition, right? This is by definition. Now I'll take an algebraic approach. Now what if I multiply both sides? So what if I multiply both sides by det of a? So what will happen here? I'll have det of a is a number, right? So I can multiply both sides by det of a. So det of a and det of a will get cancelled out. I'll get adjoint of a. Very good. Okay, this is the formula for adjoint of a. Now what is the formula for det of adjoint of a? Det of adjoint of a is det of this is nothing but det of a into a inverse. Very simple, right? Nothing very fancy here. Now this is a scalar. Remember that this is a number, right? And we have seen that det of C into some matrix A, we have seen this is C power n if A is an n cross n matrix multiplied by det of A. We have seen this in the previous video. And we can also argue this logically, right? Because what is happening here? See, we can also argue this geometrically that we have seen in the previous video, right? This is a transformation by A and I'm scaling each of the transformations by A. So the area of the parallelogram would get increased by C power n. So using the same argument, if this is my constant now, okay, if I take it out of this det, what happens now? This becomes det of A power n into det of A power, this is what it is. Okay, so this is equal to this. Now what is this? We have just seen now that det of A inverse is 1 by det of A. So this is det of A power n multiplied by 1 by det of A. See, I'm just following a bunch of rules here. Whatever rule that I learned here, I'm just applying it here. Okay, so what is this? It is det of A, because these both are numbers, det of A power n minus 1. So now adjoint of A, det of adjoint of A is det of A power n minus 1. Okay, very simple concept. There is a slightly similar concept called as a singular matrix. Let me just define it here, since we are anyway at it. Okay, I just recalled that I didn't cover this. Okay, so a matrix is said to be singular if det of A equals to 0. So what does this mean? If det of A equals to 0, this implies that A inverse does not exist. So which means a singular matrix is a matrix which does not have an inverse. Or the other way to think about it is, from a geometric perspective, that the parallelogram area is going to be 0. Or we can also think of this as the transformed I hat and j hat are linearly dependent, right? So all these concepts mean the same thing, whether you say singular matrix or det of A equals to 0, or that A inverse does not exist, or the area of the transformed parallelogram is 0, or that I1 hat and J1 hat are linearly dependent. All of them mean the same thing. Okay, so this is how lots of concepts in linear algebra can be elegantly connected. Okay, so now let's look at another concept now. Okay, slightly more intricate concept. What is det of adjoint of A? Okay, slightly tricky, but it's not too complex. Okay, now we want to compute this, right? How do we do it? We already know that the det of adjoint of A, we have seen this, det of adjoint of A is det of A power n minus 1. We have already seen this, right? So now if you think of this adjoint of A as this, right? Just think of this as one matrix, because this is a matrix, right? Using this formula, I can write this as, right, det of adjoint of A power n minus 1. Look at this. Instead of A, I'm using adjoint of A. That's it. Okay. Now I already know, see, look at this. I already know that the det of adjoint of A is det of A power n minus 1. So this is nothing but A power n minus 1. This is nothing but det of A, det of A power n minus 1 power n minus 1, which is nothing but det of A power n minus 1 squared. That's all. Very simple, right? So basically you are applying this formula twice over. Similarly, there is a very similar concept, which is det of, you can prove it very similarly, adjoint of A. This is going to be tricky. I hope I closed everything. I've closed this, I've closed this, I've closed this. You can again use the same logic here to obtain that this is equal to det of A power n minus 1 whole cube. Okay, you can arrive at this. Okay. Similarly, there is another concept, which is det of, so we have already seen this, right? Det of A into B is det of A into det of B. Again, this I can argue geometrically. What is the argument geometrically? If I've transformed a space using vector B and then using vector A, and what does that mean? The area of the parallelogram that you obtain after you have applied these two transformations, okay, is same as first apply B, compute the area of the parallelogram, then apply A, compute the area of the parallelogram. It's the same thing, doesn't change. Okay, so I can argue about this geometrically much more easily than numerically. Okay, now since this is true, what is a power k? What is a power k? A power k is a into so on k times. Okay, so if I apply this formula over and over again, what do I get? I get det of a power k, right? Very simple. Or in other words, I can also think about this geometrically by saying that if I apply transformation a k times over and over and over again, the final area of the parallelogram that I obtain is the area of the parallelogram that I obtain by applying a once, multiplied, that area multiplied k times. Okay, this is also easy to understand geometrically. Okay, I wanted to show you something else here just to get a numerical sense. If my matrix A is, let's say, A, B, C, D. Okay, imagine for any numbers. This is a simple thing to remember sometimes if you want to compute adjoint of A fast. Okay, what happens with adjoint of A is you get D here, you get minus B, you get minus C and A. So sometimes you might have to compute the adjoint of a matrix. Okay, we know the det of a matrix also, right? We know the det of the matrix. Det of the matrix is AD minus CB, right? So now A inverse, I can write it as AD. So I can write A inverse as adjoint of A, which is D minus B minus C and A, adjoint of A by det of A. What is det of A? AD minus BC. Okay, so for a 2 cross 2 matrix, if you have 4 values, you can quickly arrive at the A inverse numerically. Again, this is just the numerical interpretation. Okay, so it's easy to be, see, it requires some practice, trust me, to be able to numerically solve for adjoint of A or cofactors, minors, A inverse, etc. If you want to numerically solve it by hand, you would need to practice. In the real world, most of this is done by computers, because we don't, I mean, you could have a 10 by 10 matrix, right? And that will be like crazy hard to compute. Okay, now let's look at some more interesting properties now. Let's look at a bunch of interesting properties about adjoint, right? So adjoint of a 0 matrix is 0. Again, you can prove all of them. See, if you want to think about some of these things geometrically, think of adjoint of A geometrically as, the easiest way to think about adjoint of A is, think about it as A inverse by det of A. Okay, sorry, A inverse into det of A, sorry. A inverse into det of A. My bad. A inverse into det of A. If you ever want to think about adjoint of A geometrically, think of it as the inverse transformation scaled by the determinant. Okay, I'll just write a bunch of properties of adjoint of A, right? Similarly, adjoint of I itself is 1. You can verify all of them both numerically and some of them geometrically. Similarly, adjoint of a constant times A is the constant power n minus 1 into adjoint of A. Okay, some of these things you can numerically verify, some of them algebraically. There are 3 ways to verify some of this. You can numerically work out everything, or you can geometrically think about them, or you can think about them from a linear algebra using a bunch of formulae. Okay, I'll show you some examples here, right? Similarly, adjoint of A transpose. Okay, adjoint of A transpose is adjoint of A and the transpose of this whole thing. Okay, because this is a matrix, so this is a matrix followed by a transpose. Okay, similarly, adjoint of A inverse. Similarly, adjoint of A inverse is equal to adjoint of A, the inverse, so adjoint of A, the inverse of this whole thing. And this we can argue very simply. Some of these things, let me show you a simple example, right? So if you want to argue about this, what is the formula for this? Adjoint of A inverse, right? So what is adjoint of A? Let's write that down, right? What is adjoint of A? Adjoint of A is nothing but A inverse multiplied by det of A. So what is adjoint of A inverse? It is A inverse inverse, which means it will become A, followed by the det of A inverse. Okay, this is a multiplication. This is a scalar, right? And what is this equivalent to? We saw that the det of A inverse is 1 by det of A. So this is same as 1 by det of A into A. Okay, this is the LHS. What about the RHS? Let's look at the RHS, right? So what is adjoint of A? Adjoint of A is A inverse into det of A. Okay, if I take the inverse of this whole thing, see, remember that this is a scalar. This is a scalar, right? Let's not forget that this is simply a scalar. Okay, so A inverse is A itself, right? What is det of A inverse? It is nothing but 1 by det of A. Right? Now if you notice, your LHS and RHS are the same. So this is equal to this. So sometimes you can prove these things. This proof is using the simple linear algebraic formulae. I'm just applying the formula here and simplifying it. That's all. Okay. So sometimes you can solve some of this instead of solving them geometrically, because imagine these operations geometrically sometimes can become cumbersome. Sometimes doing it numerically is better. Sometimes geometrically it's better. Sometimes algebraically it's better. Okay. There are 3 different ways of doing it. Okay, let's look at another very interesting property. So adjoint of A into B. Okay, the next interesting property is adjoint of A into B is adjoint of B multiplied by adjoint of A. Right? This is a very interesting property. Okay, so I can actually show this to you logically. Okay, so so can I write this whole thing? Look at this. Can I write adjoint of AB? Let me solve it this way, right? Can I write adjoint of AB? Think about this as one matrix, right? Then I can write this as, from definition of adjoint, I can write this as AB inverse multiplied by det of AB. I can write it like this, right? Very simple. Okay. Now look at this. This is what I have here. On the RHS, let's see what I have in the RHS. What is adjoint of B? From the formula, this is B inverse into det of B. From the formula, this is A inverse into det of A. Now we know det of A into B, right, is not, so this will cancel out with this. This will cancel out with this, obviously, right, because these are numbers. This is a number, this is a number, this is a number. So they'll cancel out. So what do I have now? I have AB inverse. Look at this. What do I have? I have AB inverse equals to B inverse A inverse. And this makes logically sense. I can argue about this geometrically like this. I can argue about this geometrically as follows. First, I am applying, suppose I have 2 operations, 2 linear transformations, one represented by B, one represented by A. The inverse of this whole thing. See, suppose I have a vector V. I am applying operation A, right? Suppose I get U. First I apply linear transformation B. Okay. Then I apply linear transformation A. That's what it means, right? To get, let's say, W. Now, if I want to invert, what do? First I apply A inverse. Then I apply B inverse, right? See, first I apply A inverse, then I apply B inverse to get the whole inverse of AB. Okay, so to invert this whole thing, so what did I do here? First I applied transformation B, then I applied transformation A on V. This is what I have done. Now to invert this whole thing, and this resulted in W. Now to invert this whole transformation geometrically, I can argue that first I have to compute A inverse, then B inverse. Right? Very simple. That's why first I am computing A inverse, then B inverse on W. So B inverse, A inverse W is going to be equal to V. Okay. Again, here we have a nice property. Again, there is another property here, which is AB inverse equal to B inverse A inverse. This is a very interesting property of inverses of a matrices, and this can be easily understood geometrically. Right? And because we understood this geometrically, if this is true from a geometric standpoint, I can arrive at this, which means this is true. Right? Look at what I've done. The concept of adjoint itself, I'm trying to understand, I'm deriving properties of adjoint using properties of det, which have a geometric interpretation of area of parallelogram, and the concept of inverse itself, which has this inversion relationship. Right? So I hope this is clear. So if this is true, there is a very similar follow-up because of that. Okay. So now adjoint of matrix A power K, very simple, right, is nothing but adjoint of A, it is adjoint of A power, adjoint of A power K is adjoint of A power K. Yes. See, instead of A and B, if you have 2 matrices A and B, right? So instead of A and B, if you have the same matrix A and A. So adjoint of A into A is adjoint of A into adjoint of A. So if you repeat that k times, this is what you get. Very, very simple formula here. Okay. So now let's look at some more couple of interesting properties. We have already seen this, right? So we have already seen this is a very important property. AB inverse is B inverse A inverse. Similarly, there is another property which is A transpose inverse is A inverse transpose. Again, you can prove this very easily using both the numeric approach, because A transpose can easily be understood numerically as transforming your rows into columns and vice versa. Right? Very simple concept here. Okay. So these are some of the key properties, and I've shown you all the three approaches and mixtures of these approaches, where some of them are easy to prove numerically, some geometrically, some algebraically. You have to practice enough to understand which of these three you can actually employ given a problem. Okay. So this, and again, by the way, I have not gone into the applications of inverse of a matrix right here, but please understand that this is one of the most important and powerful concepts in the whole of linear algebra. Okay, it has tons of applications. There is a whole chapter in our course called the system of linear equations, where which is one of the simplest applications, by the way. Okay, so especially, I mean, in my own work and professional career, I have used inverses of matrices at tons and tons of places.